if you'll come in, you can see that she is filling the cuvette up to the line with our 0.020 molarity stock solution.
As you can see here, we are filling our second cuvette up to the marked line with a solution that we got from our dilution 1. This solution came from diluting our stock solution. Now you can see us filling our third cuvette up with the solution from our dilution 2. This solution came from further diluting the solution from our dilution 1. As you can see in this clip, we are filling our fourth cuvette up with the solution that we got from our dilution 3. That solution came from further diluting our dilution 2 solution.
She is now doing our first unknown dilution that was made with 5 milliliters of the already prepared unknown stock solution. I'm now doing our unknown 2 that we made from our dilution of unknown 1.
Now you can see us filling our final cuvette up with our blank solution.
We are zeroing the machine.
So now we're gonna hit 0.
Here you can see us taking out our blank solution and putting in our stock solution.
Our max is at 602. In order to find the lambda max, or the wavelength at which a substance has its strongest photon absorption, we must first scan across a broad range of wavelengths. Doing so is much quicker and efficient than scanning at numerous specific wavelengths, hoping to stumble across the highest value for absorption. Once we get that qualitative data, you plug that into the computer at the specific wavelength that it will then scan in order to find very specific quantitative data for the absorption at that specific wavelength.
These next clips are us finding the absorbance values of all of our different dilutions in the cuvettes.
The Beer-Lambert law relates the absorption of light by a solution to the properties of the solution according to this equation. A is for absorbance. This symbol represents molar absorptivity, a measure of how well a chemical species absorbs a given wavelength of light. B represents path length, or distance light has to travel through a sample. And C is the concentration of the sample. This is relevant because the more concentrated, the more absorbance will occur.
We zero the spectrophotometer using our blank solution in order to remove any background absorbance due to the cuvette or solvents. This is important because absorbance is directly proportional to its concentration, so we don't need anything other than our solute affecting that absorbance value. As you can see here, we have our absorbance values and concentrations of our dilutions from our stock solution. We got the concentrations from using M1V1, M2V2. Then we got our graph and the equation of the line, which we use this relationship, and our absorbance values from our unknowns to find the concentrations.
In the trash.